several books, and he gives public speeches all over the world. So things are developing. I just recall the fact that, see, I tried to show you something like laptop, and suddenly it stopped working. I have to go back to the desktop. So all these things, I think, take 15, 20 years time, everything should be obsolete. I'm trying to find the industrial here. Thank you. So are you ready for the Easter break? You have a lot of assignments to submit? Are you doing a lot of assignments these days? No. Okay, so let's go ahead with some of the basic concepts before we test for unit 2. These are very simple stuff, and I have explained to you in my first or second lecture about non-stationary time series. There are some concepts which you will very frequently use while doing unit 2 test. One of them is called random walk. And random walk of a time series represents the behavior of the time series which has unpredictable pattern from period t to t plus some. So it says random walk and unit 2, they are used synonymously in literature. From the term random and random walk, you can understand that if somebody drinks a lot of wine or some alcohol, and then you ask him or her to walk straight. So what type of behavior do you think you will see? That if somebody is drunk heavily, and then you will ask him or her to walk straight. So that gentleman or lady will not be able to walk straight. There will be some pattern. He will go this way, and suddenly he turns to the right, and then go straight, and then probably again right. So there is no specific pattern. You cannot predict any specific pattern with this one. This is what the random walk. Walk that is random, not prefixed. Okay? So there are some time series which have exactly the same type of pattern. For instance, let's think about the stock prices. That's the same example I give you. So say for example, it was going up like this, and suddenly it rose due to some news. Then suddenly it fell. Okay, and then it was going for some months before there is an election which brought some positive news for the government and the economy. It rose up again. Then again plummeted. So something, there is no specific pattern. So then this is a kind of random one. Say here, if you want to draw a trend, you won't be able to draw that one. Because the pattern of the movement of the series is so random, so unpredictable that you cannot do. I mean, in which direction it might go, you cannot predict that one. That's why it's called random walk. So random walk is almost the same kind of thing like a unit, but with a specific limitation. Say there will be, for a random walk, you can just write yt equal to alpha plus say beta yt minus 1 plus epsilon t. Here you can just use beta, rho, whatever you like. One thing is that you can use either intercept or no intercept. If you don't use any intercept here, you can just write yt equal to rho yt minus 1 plus epsilon t. And here, in this case, rho equal to 1 means it can go in any direction. Now, one more thing before I tell you how to test for unit 2. One small thing that you should be aware of. You know, you have not asked me yet why this is called unit 2. You have not asked me. We have done 4 hours of lecture on unit 2 and non-stationarity. But so far, you have just listened to me. But you did not bother to ask me why, sir, this is called unit 2 process. Why this name unit 2? Can you reflect on this one? Anybody? Why this is called unit 2? instead of unit root, we could have called, okay, non-stationary series. Why this is unit root? So this means, my friends, only listening is not enough. You must ask me. If you have some doubt, just don't be listener. Ask whatever comes to your mind. Okay. The name unit root comes from a very simple fact that I don't know if you have done some sort of difference equation and differential equation at some stage of your courses in mathematics or statistics. Have you done something called difference equation? Or differential equation. Have you done them? No. Even if you have not done, that's fine. So these two things actually refer to how to detect the behavior of a time series using mathematical methods. So in our simple case, say yt equal to rho yt minus 1 plus epsilon t. Whenever we have lag 1 and it is the linear form, so we call this a linear difference equation of first order. We call first order difference equation, lag 1 in the linear form. So to know how this series behaves and to predict some pattern, we can make a solution of this equation. We call this first order difference equation. First one difference equation. And then there is a solution to the equation. One we call complementary function. Plus particular integral. These two things, particular integral. So both of them give the general solution. General equation, general solution of any difference equation. It has two components: complementary function plus particular integral. When you don't need to know all the mathematics at the moment, but whenever we solve the equations, especially in particular integral, we come up with an equation which says the root of the function. Root. Okay. How do I find a root? Can you find out the value of x from here, please? Yes, you have an equation, x squared plus 4x plus 6. How do I find the value of x? It's a quadratic function. How do I find this one? And
No.
so I can write like, what can you tell me?
2.
So x1 or x2, like that. You can have two values of x here. So how can I write plus minus? Is it like that?
Yeah.
Minus b plus or minus
Minus b.
Yeah.
plus or minus square root
Something
b
like this.
squared
B squared minus
4ac.
How do I write here?
2.
2b.
2.
Is it minus b here?
Yeah.
No.
Yes. So, do you understand now? So, based on whatever you have, that's not an important thing. B square minus 4AC means A and then the constant. So if this one, B square is greater than 4AC, then you have the real number. If this is less than 4AC, we have imaginary numbers. So based on those things, you can have one value of x and another value of x, for one plus plus, one for minus. And those values, actually they are for the root of the equation. And some of the roots, these roots, can be something like this. If the root is equal to or greater than 1, then this is what we call explosive cycle. If root is less than 1, we call damped cycle. So, unit root is a concept that we have derived from differential equation and differential equation as a solution to a time series equation like that. Y is equal to this, then this is actually, this can be represented in terms of, yes.
Saying the b should be upper than 2a.
Sorry?
The b, I mean, the solution for x
Yes.
is upper to a.
Yeah, yeah. So, this one you can always translate this one into a differential equation form, and then the solution of the differential equation, if one of the roots is greater than or equal to 1, then and if you plot it across all the values of that value, then the root can be, it can just go up. It's something called explosive cycle. It never returns to its mean. But if it is less than 1, just like root less than 1, and then we can have a damped cycle. Over time, so t here and the root here, over time, it all converges. So that is the basic idea. Why this is called a unit root. A unit root represents the behavior of a time series where the root of the equation is always explosive, moves away over time. This type of explanation will never be given in any textbook. You find any textbook, normally they don't give this type of explanation, but you should know. You ask this question to any econometrician and in any top university also, probably they won't be able to tell you why this is called a unit root. They can tell you all the properties of unit root, there are different testing procedures, but how this has been derived, based on which principle, they might not be able to tell you exactly based on the differential equation. Only in some advanced textbooks, very mathematical textbooks, sometimes they do. So this is about the random one. And then the second one is about the integration of a time series. So we call this order of integration called ID. So what it says, if you can write yt equal to, say, alpha plus, forget about the intercept of the, say, rho yt minus 1 plus epsilon t. And if we think the original time series, original variable is non-stationary, and then you can take the difference of the variable, means take away yt minus 1 on both sides of the equation. So you can write yt equal minus yt minus 1 equal to rho yt minus 1 minus yt minus 1 plus epsilon. And so this becomes, I call this one as delta yt. Delta represents the first difference. T minus 1, I call it first difference. So this one is rho yt minus 1 plus, so this will be rho minus 1, yt minus 1 plus epsilon. This triangle you see here, we call it first difference. You can write this one as 1 minus L. L represents the lag. I told you about that. If I say write LYT, I call it YT minus 1. L square YT, YT minus 2, L cube. So just see, LYT, L means lag. So 1 here, so I write it YT minus 1. Square YT equal to YT minus 2. Likewise, you have LP here, YT here, so YT minus 2. Okay, so this is about the lag. And in this case, I can write this one just to simplify. If you are not convinced how it looks like, so I can write it as YT minus 1. Following this, I can write it LYT equal to this. And so YT common I have, so I can take YT common and then 1 minus L. Okay, so then rho minus 1, YT minus 1 plus epsilon. So this 1 minus L, I can call this as delta. Call this one the delta. So delta YT. So in this case, whether you call it delta or 1 minus L, its power in this case is 1. Okay, so I write it 1 minus L YT, or the same, which is same thing as delta YT. In this case, I say degree of integration means what is the order at which the YT is integrated. So in this case, D equal to 1, D equal to 1, which is just the converse. So when D equal to 0, it comes down to power. Okay, so whenever D equal to 0 or D equal to 1, so this refers D equal to 0 means 0 degree of integration. That is stationary shape. And this is unit rule or non-stationary shape. Okay? So these are the fundamental concepts you should know. So D equal to 1, non-stationary or unit. Normally, what we always want, we want to have a time series which is well behaved. Means it's a stationary all the time. If a time series is not stationary, what type of problems do you think it can give rise to? We are trying to learn about non-stationarity of a time series by testing it with unit rule procedures, all that stuff. But imagine in contrast that the time series is stationary. So with stationarity assumption, you derive all these conditions of the OLS, that the estimators should be consistent, unbiased, efficient, all those things you have learned about least square estimation. And the error term is IID, normal. So normal error term, independent, identical distribution of the error with mean 0, constant variance, all these things will break when a time series is non-stationary. I told you before, for a non-stationary time series, the standard distribution, the distribution of the error term is non-standard. It is non-stationary. It is not Gaussian. Second, that you may not have zero mean, because we have derived in 3 cases, drift, trend, no drift, trend. In each case, we have a constant mean, but that mean may not be 0. We may not have 0 mean, but this mean can be some 1, 2, 3, any value greater than 0. And second, the variance. In this case, we have seen the variance for unit root case t sigma square, when limit t tends to infinity, that tends to infinity as well. So basically, there is no limited variance. So that assumption about that the least square estimations are blue, best, linear, unbiased, and efficient estimator. Efficiency means minimum variance. So that minimum variance assumption is broken. There is no minimum variance. What we see here, when time series has unit root, rho equal to 1, when rho equal to 1, variance is infinity. So minimum variance minimum variance does not work. So all the assumptions about classical econometrics breaks. So that's why from 1970, when Professor Fuller and Dickey, they introduced this non-stationary econometrics, it was almost like a paradigmatic shift in the way we understood econometrics. So there was, in one case, a stationary econometrics, one world, and there was this non-stationary econometrics, another one. And but hardly in real life we find a series or time series, because in any case we are dealing with number of variables which are time series, observed over time across cross section. So in almost 99% of the cases, we are bound to find the properties of non-stationarity. So the classical theory of econometrics, its scope is now limited. Although we must know those assumptions, what do they mean? Otherwise, how will you know what they do not mean here? Okay? So this classical econometrics does not work now. I don't know if I had told you before, but I was probably mentioning in Kuhn's PhD lecture, the kind of econometrics you know so far. Do you know how much you know? I mean, at least me also, it applies to me as well. In econometrics, you can have classical and Bayesian. Both can be stationary and non-stationary. So again, within both of them, there is parametric and non-parametric. As an economist, econometrician, we are somehow, the Bayesian econometrics, this part, you will never touch. You are not doing anything now. Okay? We are doing classical, mostly stationarity, parametric for sure, and some element of non-stationarity. So, half of the world, we have no knowledge of econometrics. We are not dealing with them. Only here, classical, we have done stationarity, but we will be studying a bit of non-stationarity, only some tests, and the parametric domain. So non-parametric, against stationary and non-stationary, Bayesian, those things, those entire one, we have no idea about. We don't know. So this is our world. This is what we are learning about now. So now do you realize now that wherever there is a non-stationarity in the data, the variances are not minimum. So there is large infinite variance, and so this case will apply when you can say, on the other hand, d equal to 1 implies that delta d, so equal to delta d equal to 1 here. That means a series has unit root. Say xt, any series x or y, yt has unit root. If d equal to 0, so delta d, so equal to 1, 0, anything to the power 0 is 1. So yt is stationary. But there are some extreme cases, these are the extreme cases. D equal to 0, d equal to 1. But the world does not act like this. So you are either you are with me, either you are my friend or you are my foe. It doesn't happen like that. So there are some in-between cases, like d can be greater than 0, but less than 1. And this type of thing, we call it long memory. Once again, for your lectures, at least for your given the scope of your subject, we will not learn this. We will just test for any time series whether d equal to 0 or 1. And this long memory time series, if you are more interested, you should read some good textbook where I have mentioned. There are some in Anderson's books and Ender's book. There are lot of stuff. So this one represents the most practical, realistic view of the time series. You know why? You cannot find a time series which is completely stable for all time to come. And we cannot find somebody which is always non-stationary from day one to day end. We always try to find time series or individuals or agents or systems or economies which are stable for some time, then they are subject to some random shocks. Then after some transformation, they come back to the original level. So it happens all the way. So stationarity and non-stationarity, both components can be characterized in any agent's economic or financial. So this is the reality. The reality is a series over time can behave both stationarity for some region, non-stationarity for some region or for some time. And this is what we call long memory. A very good example of long memory. I always give this example in every class. Cole has also heard. And the long memory, the way we describe, just I gave you this example. If you are separate them on the road, somebody gives you a tight slap, and if you are a forgiving person, so what you do that you forgive and forget. So that means b equal to 0. But it might happen that you are a very, you want to take revenge at some point of time. So after 5 years, I gave you a slap. So after 5 years, you see me on the road, you slap me back. Okay. So this is b equal to 1. But in between, so you saw me after 5 years, so you are still angry with me, but you have forgiven for somehow. So d can be less than 1, but greater than 0. Okay. So that is how shocks, okay, to any time series. So over time, this is epsilon t. So t equal to say t equal to 1 to say 10 years here. So what happens over time? So maybe at 7th year, you forget all the shocks and numbers. Okay. So this is what we call the long memory. But you will not study this for the moment. But remember all this technical stuff before we part from the test procedure for you. Okay. So this is what I have mentioned. So you can see when a series is I1 means I1 represents I b equal to 1. So integrated of order 1. Yes, and so that is some kind of unit root or non-stationary. So in general, a series can be ID, where d can be equal to 0, d can be equal to 1, d can be greater than 0, less than 1. In general. So this is what we call ID process. Okay. And so there are a couple of cases I have mentioned. D equal to 0, yt is I0, stationary process. D is greater than half, but less than half or equal to half, greater than 0, we call it a covariant stationary process. So these are a couple of processes that you should know. Now with those things in mind, let's try to see how we perform a unit root test. One of the simplest ways to detect whether a series is stationary or non-stationary is to look at its autocorrelation function. Okay? Before doing any formal test of unit root, the way we do. So informal test of unit root. And that one is called ACF, autocorrelation function. What is autocorrelation function, by the way? Auto means self. Correlation with self. So that means if you have error term at time t, and then its correlation with the past value, this is what we call self, correlation with self. So rho here. Okay. Rho means the correlation structure between ET et minus 1. Similarly, you can have et minus 1, et minus 2. Correlation between them. Et minus 2, then et minus 3. Likewise. And then we can plot those things. So you can say here, so this is your time, this autocorrelation function, we call ACF. And then we can see over time is the correlation, okay, how fast it is declining. So for example, from 0, t equal to 50 years ahead, and if the stock prices, it shows that even after 50 years also, the current and past values of the stock prices, it is still declining, but past has some strong effect. This is the current value. So this is what we call how we plot the autocorrelation function. That means the correlation between t minus 1 values of the time series. So over time, so each point represents the correlation here, all that time. So over time, the correlation between the successive values, t minus 1, t minus 1, t minus 2, 2, minus 3, minus 3, minus 50, likewise here. So if the correlation declines, but declines very slowly, and that type of behavior we call unique. In case the correlation declines very fast, say after 3 periods, it is just ancient. So that type of behavior we call stationary series. If we have data for say 100 years, but we saw that only what happened 3 years ago, only it affects now. This is quite consistent with different types of finance and economic theories. If it is so, then there is what happened the last 100 or 97 years, 50 years, does not affect the current value of the YT. So this is stationary series. And so whenever this goes like this for over time and becomes asymptote, so this is what we call d equal to 1. I will show you some graph related to that here. It is all in the lecture note. Let's see. Just have a look. In this graph, the first one is a time series, the plots of the time series. And I have already explained to you that this time series, it has 2 important characteristics. You can see that this is the stock price series, which has from some different months, from 0 to 500 months. From here to here, we have one mean. From here to here, another mean. From here to here, another mean. From here to here, another mean. So there is a non-constant mean. Now, this ACF means autocorrelation function. That means the correlation between the succeeding values of the time series. You can see that from period 1, 2, 3, 4, 5, 10, then you just go on like this for over time. And there is very little tendency of the correlation to decline. It remains almost the same, little by little, but it might take 100, 200, 400 years, we never know. So that type of correlation is the representation of a random walk or a unit behavior. Okay? But in contrast, using this one, if it is a stationary time series, so then for a stationary time series here, this one, falls. Suddenly, maybe 2 years or 3 years, like that, any 2-3 years time period, and the autocorrelation completely disappears. So that means epsilon t had some correlation with t minus 1. Epsilon t minus 1 with t minus 2. After that, epsilon t minus 2 has no correlation with epsilon t minus 3, likewise epsilon t minus 50. Whatever time length you have, no correlation. Okay? It's okay? You have some question?
Yeah, we can ask this, why is it called random walk if the correlation is 1?
Yeah. So, no. Correlation is not 1. Okay, a very good idea. Let's explain how. That's a very good idea. See, this kind of thought always asks you to think more. Okay, your friend thought because it's a random walk, so the correlation can be also equal to 1, can be. Let's think about this possibility, okay? Very good, I appreciate that. So, how do I write correlation function? Just last time you told me, that correlation, say, let me say this is a row equal to between 2 time series. So, in case, yes. So, let's say I have et and et minus 1, or I have xt minus 1, a variable xt and say t minus 1. Right? So I can take covariance of xt, then xt minus 1, then I have variance of xt times variance of xt minus 1 square. Okay? This is a correlation. So we know that correlation coefficient can be, it lies between perfectly positive to perfectly negative. Okay. So if equal to 1 or equal to this one, anywhere in between. So perfect positive correlation means that xt and xt minus 1, the dependency is just perfect. So that means whatever is happening here is completely reflected here. Then if I have xt minus 2, xt minus 3, likewise say xt minus 50. So it implies that correlation between xt minus 1, t minus 2, also 1, t minus 3, and t minus 4, 1, and t minus 49, t minus 50, also 1. If they are all 1, that means that xt minus 50 and the correlation between xt, that is also equal to 1. Because 1, 1, 1, 1, 1, 1, 1, everywhere, so this is equal to 1. But we have forgot one small thing. That is, it is not just about the correlation. You remember that whenever we write xt minus 1, I am also adding something here. That random component will allow you to experience not so perfectly positive autocorrelation. So that is one reason that you can see these graphs, it has a tendency to come down, slow down little by little, but maybe 0.00001, 0.0003, like that, coming down little by little. But this slowness means that it might take 200, 500, 800, 900 years so that the autocorrelation can be possible. So that's why for a random walk or unit root process, the autocorrelation is not always equal to 1. So you can always rest assured, you can always say that rho equal to 1 minus epsilon. That value of epsilon, you have to always be that. But because it's a random walk, that's why if it is 1 minus 0.001, so you will have 0.99 something, 999, something like that. So then 0.998, 0.997, likewise, over time. So we have to always take into account the value of that epsilon. So that's why, but whenever we are assuming that xt minus 1 completely affects xt, I am assuming no role for epsilon. Epsilon t has no role. Is it clear? Okay. So for any equation like this, whenever I am talking about correlation, xt minus 1, and in that case, if I do not take into account the role of epsilon t, then it can be perfectly positive. And you may be right. Fine, maybe. You must be right. Is it clear now? Yes. Kun, is it okay? So, if somebody asks you what can be the correlation coefficient for a unit root process, so you can say that it can be perfectly positive or negative, in both directions it can go, plus minus epsilon. So with that epsilon value is adjusted all the time to potential. So whenever you see any time series, then before you do any formal test, which I will do after the break. So the first thing you can do is to plot the time series, okay? And from the time series, you can see the mean and variances from the upper part of the graph. You can see the mean and the variances of this graph are non-constant. And you have seen this one before as well. See, I have, remember that one. The mean is non-constant, the variance is exploding. I explained that at the beginning of the lecture last week. So there is no constant variance, no constant mean. So that means whenever you have a time series which is trending up like that, so its mean here, 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 and here. The means are shifting always. Non-constant mean, non-constant variance. Along with that, you can say the autocorrelation function is also declining extremely slowly over time, which says probably the series has a unit. So from inspection, visual inspection, before doing any formal test using different procedures, you can just have a look, just like any GP. You go to a doctor and you want to say, sir, I might have a heart attack. But before saying whether you are really suffering from that, the GP would like to test your nerve and pressure, these, that. Very basic stuff. So these are the basic stuff. Do basic check. Whether you really can say the series has a unity. From this, after this inspection, now we'll go for the formal test procedure after that. Take 5 minutes break, we'll come.